Hi, in this episode we're going to discuss alpha rays and how the alpha ray scattering experiment helped us understand the atomic structure much better than the cathode and anode rays experiments. And alpha ray scattering experiments were initially done but were not analyzed until Rutherford came along, and he was a student of Thomson, and ironically, the Thomson's model was shattered by the alpha ray experimental data by his own student. We'll investigate what occupies most of the atomic volume, what is at the center of the atom, and how the atomic structure has been understood with these new revelations. And so Rutherford was a very good experimentalist and analyzer, and he analyzed a large body of data that was already present and on alpha ray scattering experiments. Alpha rays are the rays emitted by radioactive material and later were found to be helium nuclei. These are emitted when a nucleus disintegrates. The radioactive reactions produce alpha rays or helium nuclei as byproducts, and these are ejected from the nucleus. And so, for example, radium, which was used not too long ago in watch dials, emitted alpha rays. And so these are helium nuclei, highly carcinogenic. And they, of course, the only grace was that it could be readily stopped by matter, a few centimeters. They could only pass through a few centimeters, perhaps, not too long in matter. So in any event, the experiment is the following. You have a source of alpha rays on the left in the box. The blue line indicates the alpha ray particle, which is helium nucleus with the two positive charges on it. We know now that, not at that time. And a gold foil is put in its path. A thin gold foil was put in path. And the gold foil had no holes in it. It is complete, clear gold foil. A complete opaque gold foil, and with no holes in it. And alpha rays pass through as if it didn't exist. And this was recorded by a photographic plate on the right-hand side. And occasionally, there are a few alpha ray particles that were reflected back or deviated from the original position, but very few. Occasionally, a particle came back, bounced back, almost back into its position. This is again recorded by a photographic plate. By placing a circular photographic plate around the gold foil, they were able to detect that the electrons are scattered. If the particles are scattered by very few of them, scattered by very large angles. So the following are the observations. Alpha ray particles from radium pass through the gold foil as if it didn't exist at all, as if it has big holes in it. And so large, it should be visible if the holes are so large. But yet, you can't see any holes in the foil, but the particles pass through it. So that was a big question. What is the reason? A few particles occasionally scattered through very large angles. What do I mean by this? Let's say you have the atom written like this in a few circles with a plus charge in the center. The particles passing through the atom as if nothing existed in the atom. Until one of the particles, for example, approaches very close to the nucleus, and then it is suddenly deviated by a large angle. Even one of the particles, when it arrived, it's a head-on collision with the nucleus or the positively charged center, turns back nearly 180 degrees, and so that can be detected. So only occasionally this particle returned very rarely, but then it returned at very large angles, nearly 180 degrees. And so this was kind of surprising to Rutherford. And so this was known for a while, and then Rutherford came along and explained this. So this suggested, he said, a heavy, small, very small inside of an atom, positively charged mass at the center. And so he said this in his quote. This is reproduced verbatim. If you fired a 15-inch shell at a piece of tissue paper and it came back and hit you, it was then that I had the idea of an atom with a minute, massive center carrying a charge, unquote. So this was his explanation of the observation. And from this observation, already he explained his reasoning for this observation, that minute, massive center carrying a charge. So that's the data he inferred from this. So it's a wonderful experiment, beautifully done, and very well analyzed and concluded. And all that is correct. So the conclusions then, there are large spaces in the atom, occupied nothing. So you ask, what is there? I mean, how can the atom have large voids? And positive charge and most of the mass are at the center of this small volume. Why it has to be all the mass? Because there is nothing stopping the positively charged particle until it actually hit dead on with the center of the atom. So, and then the recoil is so massive recoil that and the particle bounced back. As you said, a 15-inch shell was fired at a tissue paper, it bounced right back and hit you. So that means that center has to be very massive and should have the same charge as the particle. And because only few particles are reflected back, that volume of that center must be very small. So from the ratio of the particles that pass through and divided by the number of particles were essentially recoiled back, he was able to calculate the diameter of the nucleus to be at least some 4 orders of magnitude smaller than that of the atom known at that time. And so that's why it's called minute, massive center. Minute, because it's almost 10,000 times less. Or you can actually look at the actual data and tell me exactly what the number is. And so it has to be extremely dense material because most of the mass is present in a very, very small volume. So what is the density of the nucleus? You can find that out. And so most of the mass and the charge, positive charge, are at the center in a small volume. And this was labeled then as nucleus. And then that stuck. So nucleus. And so his model replaced Thomson's model, but was not really better. It has its own problems. Nucleus is then immersed in a cloud of negative charge. It's a cloud because particles pass through. There's not necessarily much mass associated with it, and things can pass through this cloud. It has to be negatively charged to balance the charge on the nucleus. Stability of the atom could not be explained because how could you have a negatively charged cloud with a positively charged center? So his paper mostly described the nature of the nucleus and its mass, its volume, its position, etc. He completely avoided the issue how the negative and positively charged particles are arranged. Thomson's model was very attractive, plum pudding model, very attractive. One could visualize where the positive charges where the negative charges. But the Rutherford's model couldn't do that. So the location of the electrons, as many electrons as needed, depending on the atomic number of the element, could not be ascertained. And so he didn't talk about the position of the electrons to begin with. And how could you keep the electrons and nucleus apart if they have separate charges? You can't ask them to stay put at faraway distances. And so that was an anomalous behavior that could not be reconciled. And so then, so you have a nucleus at the center, and then the cloud of electrons surrounding that. Then it was suggested that the electrons may whirl around the nucleus like the planets around the sun in our solar system. And so this is a gravitational model that was supposed to be operating in the same way as the atomic model would. So it's very appealing to people to think that the nucleus is the sun, and the electrons are the planets, and so the planets go around the sun but not fall into the sun. Same way electrons will go around the nucleus but not fall into the nucleus because they're rotating around. So the centrifugal force, it will keep them apart and work against the electrostatic attraction towards the center. And so they thought the planetary model of the atom is pretty appealing, pretty neat to think about, like the solar system. But the only problem is Maxwell's electromagnetic theory predicts that when an electric charge is accelerated, it should emit radiation. It should emit its energy as radiation, as electromagnetic radiation. And this is how we generate radio waves and microwaves and so on and so forth. And so it is very well understood by that point that when an electron is going around in a circle, it is being accelerated towards the center. So the charge and acceleration of a charge should produce electromagnetic radiation. So the circulating electron should emit electromagnetic radiation and lose its energy. As it loses its energy because of emission, then it will move closer to the center, and eventually the electron should fall into the nucleus and destroy the atom. So this is what is called the catastrophic destruction of the atom due to radiative emission of the electron's energy, as predicted by the Maxwell's electromagnetic theory. So making the electrons go around the nucleus made matters worse. And so Rutherford's model was kind of explained half and could not explain the other half. And also couldn't explain the atomic spectra. And so there was no resolution to this problem. And so this is the planetary model that is showing on the right side. So it's born out of Rutherford's atomic model. And of course, Bohr picked this up and gave a lot of substantive evidence for this sort of thing, which is still incorrect, but still it's very popular because of its nature. And so in summary, the core of the atom was found to be massive, dense, and repelled alpha particles. Very few particles were repelled compared to the ones that passed through. So the core was thought to be positively charged, and this was later showed to be correct, and because later alpha rays were found to be positively charged. Just like cathode rays and anode rays, the alpha rays were also examined, their E over M ratio determined, and so then it was known that they are positively charged, and therefore in the alpha ray experiment, the nucleus must also be positively charged in order to repel the alpha rays. Hence, the core could also be positively charged. The core occupied a very, very small volume, 10 ppm on end of the atom, and the electrons should be occupy the rest of the volume but have very less mass. This model was unstable because the electrostatic neutrality is maintained, but how to keep the charges apart from coming together and so they could not be explained. The atom should shrink down to nothing and destroy itself. And so it also couldn't explain the atomic spectra. So the stability could not be explained, the spectra could not be explained, the location of the electrons could not be explained, and one could not explain how the positive and negative charges are arranged. And later you'll see that Rutherford's model, after all, is correct. And we will see that when we go into the Schrodinger's model. So now explain why Rutherford's model was thought to be correct. And you can answer this and post it to the discussion board.